Everybody say hi, Libby.
Hi, Libby.
Okay, so we are starting chapter 2, and this is the homework assignment for 2-1. It is out of the book. There are a couple times throughout this chapter that we will be on worksheets, like when we're doing graphs and stuff or whatever. But this one's out of the book. I am not going to lie to you. Chapter 2, you're not going to like very much.
Great.
But section 2-1 is pretty pleasant. It's not too bad yet, okay? Yes. But you're not going to like the end of chapter 2. It's not going to be very much fun. It's like introduction to proofs, and you're not going to like that very much, okay? So there's that. All right, so conjectures and counterexamples is what we are doing today, all right? And there is not a backside on your note sheet, evidently, except it didn't get photocopied. There is a last example on the backside. So I'm going to have you guys add this to your backside sheet. Sorry, it for some reason didn't get photocopied. Okay, so 2-1, this is kind of fast, so we'll go speedy fast. Inductive reasoning is the first vocabulary word that we have. And they have inductive reasoning, and then later on in the chapter, we will talk about deductive reasoning, okay? So here's what inductive reasoning is, okay? I see the word in, and it means you're putting stuff in. So in inductive reasoning, you have a pattern of things that you're putting in to a conclusion. So you're forming a conclusion. You're forming a conclusion from a pattern or a group of behavior, okay? So you take that pattern and you're shoving it into some conclusion, okay? And that conclusion is called a conjecture. Okay? So I told them this morning that probably what's going to happen at the end of this chapter when we take a test is we're going to have a question that says, make a conjecture about this thing. And I guarantee you that Chase is going to come to me and say, what's a conjecture? Guaranteed. Okay. And he's like, I will not, now that I know, right? So I'm like, okay, what's a conjecture? And he still couldn't tell me. I'm like, it's written right next to the number. All right. So, or right next to the thing. So a conjecture is just a conclusion about some certain behavior. Okay. So that's what a conjecture is. You're just making a statement about some things. All right. Example 1, we have patterns and conjectures. Write a conjecture that describes the pattern in each sequence. Then use your conjectures to find the next term in the sequence. So the first thing we have to do is identify the conjecture. And then the second thing we have to do is find the next term in the sequence. Okay, so we have 2 answers to this question. Make sure that on your homework assignment you answer both parts of the question. And they're saying that the movie show times are at 8:30 a.m., 9:45 a.m., 11 a.m., and 12:15 p.m. What is the pattern? That's our conjecture. What is the pattern? What are we doing?
An hour.
Shows are 1:15 apart. I'm just going to say something like that. Show times are 1 hour and 15 minutes apart. That's our conjecture. Okay? The next show time would occur at 1:30 p.m. See, this is not hard. Okay? Good?
Yeah.
All right? Okay. Let me draw this one and then I'll help you. Part B. They have numbers and then they have this like a geometric kind of pattern going on here. Okay, so we have 4. Do you see where they get the number 4 from?
Yeah.
There's 1, 2, 3, 4 sides on that box, right? Okay. Then this one has 10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Mm-hmm. That's like where the 10 is coming from. Okay, so let's draw what the next one looks like. Okay. So we've got like a little bit bigger, something like this. Okay, and we have a 1 by 1 and a 2 and a 3 and a 4, and I draw this really terrible. 1, 2, 3, 4, and then we've got a 5. So 1, 2, 3, 4, 5, and this is like the 6th ring going out, right? The 6th ring going out. Yeah. Okay. All right, then we have to figure out like what this number is, okay? So I'm not going to count each one of those. Let's look at what we're doing each time. So like from 4 to 10, how many did we add? 6. And from 10 to 18, we added 8, and then we added 10, and then we added 12, and now we're going to add 14. And so this one has 54. Okay, so our conjecture, we've figured out the next term. Okay, that's what the next term is. The next term is 54 and the diagram. But then what's the conjecture? We said this morning that you're adding, but you're not adding the same number every time. You're adding n plus 2, like the one right before it plus 2 more than that, right? We just said adding n plus 2 to each term. Does that make sense?
Um,
Yeah? Are you trying to line something up?
Mrs. Brown wants to know if this is straight. Yes.
Okay, can you wait just a second?
Yeah.
I'm recording, otherwise I just stop. But anyway, okay. Conjecture. You're adding n plus 2 to each term. Good? Okay, moving on. All right, let's go to the next one. Make a conjecture, so a guess, about each value or geometric relationship and list or draw some examples to support your conjecture. So we have our conjecture, and then we have some examples to support that. Okay, so part A says the sum of two odd numbers. Layla came home Friday, and she said, hey, Mom, did you know that the sum of two odd numbers is always even, right? And I said, yeah, did you know that the sum of two even? So I told her this. I said, did you know the sum of two even numbers is also even, right? And she's like, what? I said, yeah, the only time you'll get an odd number is when you add an odd number and an even number together. And so I'm like, in first grade, she's already figuring that out. So anyway, the conjecture is, I'm going to do this in a different color. The sum of two odd numbers is always even. Examples? I don't know, like 5 plus 7 is 12. Give me some more odd numbers.
1 and 3 equals 4.
1 plus 3 equals 4. These are even. Okay. What else? Give me one more.
3 and 5.
3 plus 5 is 8. And those are even numbers. So look, hey, they're all even. Even numbers. And these were all odd numbers that we were adding together. Odds. Right? So there's my example. All the odd numbers, when you add them together, is an even number. What's the sum of three odd numbers going to be? Always odd, right? Okay, anyway. All right, segments joining opposite vertices of a rectangle. This is a little bit confusing, okay? So let's talk about a rectangle. Let's draw a rectangle first. And what does opposite vertices mean? Like the corners that are across from each other. And the segment that joins those, okay? So I'm going to draw a segment that joins those two. And I'm going to draw this in a different color. I'm going to draw a segment that joins those two, okay? So what are some things that I know, or what's one thing that I know about those two segments? These are called diagonals, by the way. Diagonals. What do I know about, or what can I say about the orange diagonal versus the green diagonal? If it's a rectangle. The orange diagonal versus the green diagonal. That's my conjecture.
They always cross in the middle.
They like bisect each other. They always cross in the middle. Yeah, so that's it. So I'm going to say the diagonals bisect each other. Do you guys know what I mean by bisect? Okay, they're splitting each other into two equal pieces. So it's cutting it in half. But what's one other thing that I can say? What about the length of each one? They're going to be the same length, right? So the diagonals will be the same length. And I had Luke, of course, was saying, well, isn't that true out of every like four-sided figure? I said, okay, well, like if it's a square, will those diagonals be the same? Yeah, but what happens if it's like a parallelogram that looks like this, right? Will this be the same as that? No, one's going to be longer, right? Okay. We discussed that a lot more in detail in like chapter 4, I think, something like that. Okay. So there's that, right? Okay, example 3. The owner of a hair salon collected data on a number of customers her salon had each Friday, Saturday, Sunday for 6 months to decide whether she should increase the number of stylists working each weekend. Okay, she collected this over 6 months, okay? So I don't know if you can read this table, but here's Friday, Saturday, Sunday, and month 1 through 6. So in the 5th month, how many customers did she have on Saturdays in the 5th month? 746. So we just kind of understand how we read this table. On Saturdays in the 5th month, all the Saturdays together, she had 746. We are just trying to decide, using this information, is there a pattern? Do I need to hire more people? Okay. What do you think? Do we need to hire more people? By looking at this data. What? Saturdays are always more, right?
Yeah, because everyone's off work.
Right.
Fridays always have less.
Fridays always have less, okay? In general, if we just look at the totals over those past 6 months, Okay? It's increasing steadily and it's never decreasing, right? Okay? So if this pattern continues, are we going to need to hire more people to work? Yes. So general conjecture is yes, hire more people. Okay? I feel like this is kind of like, I don't know, easy patterns to figure out, like, kind of just decision-making things. Okay, good. Yes, hire more people. Just looking at the trend over time, right? Okay, happy with that? Okay, go to the backside. And you guys don't have a backside, so just put this down here. Write the word counter example. Write the word counter example on the backside at the top. Okay? And a counter example is a statement or is something that proves a statement false. Okay? Something that proves something. I just didn't. Oh, yeah, I did. I wrote that right. Something that proves a statement false. Okay? All right, now, this counter example can be a number. It can be a drawing. Or it can be a statement. Okay? It can be a number, a drawing, or a statement. Okay? So I used the example this morning, and I said, if I told you right now that it is raining outside, you'd be like, Mrs. Comacher, no, it's not. I'd be like, yes, it is. And you'd be like, no, it's not. And I'd be like, yes, it is. And I'd be like, no, it's not. And you're like, okay, I'm going to prove to you that it is not raining outside.
That's like arguing with Luke.
Right. Yes, exactly.
Okay.
Like, but it's raining somewhere in the earth.
Right. Yeah, that's literally Kyle's argument this morning. Kyle's like, but did you know there's like 1,000 thunderstorms every day during your... I'm like, I don't care.
It's like, I don't care.
So I'm going to say it's raining outside. You're going to say, no, it's not. I'm going to say, yes, it is. You're going to say, no, it's not. I'm going to say, yes, it is. And we're going to go back and forth like, nah, yes, nah, yes, right? Okay. And then you're going to say, fine, Mrs. Comacher, I'm going to prove to you that it is not raining outside. I'm going to walk outside, stand there for a couple seconds. I'm going to walk back in, and you're going to look at me and say, there is absolutely no drops of water on you. And that is my example to you saying that it is not raining outside. You are proving me wrong by using the counter example that you are dry when you come back inside. Does that make sense? Okay. So that is like a statement of a counter example. Like you're saying to me, I'm going to come back inside and I'm going to be like completely dry, and that's how I know you're wrong, right? You're just proving something wrong, okay? So there's an example of that. It's just like you're trying to like show me why I'm wrong, okay? So here's two things that we know that in most of the time that they are true, but we're going to find a counterexample that proves it false, okay? So part A says if n is a real number, write this down. If n is a real number, then n squared is greater than n. Okay, and that's the first thing that we're going to make a counterexample of. If n is a real number, so n is any number that you can think of, then n squared is greater than n. And most of the time, that's true, right? Like if n equals 2, then 2 squared is greater than 2, right? That's true most of the time, okay? But is there ever a case where if I square some number, it's not bigger? Give me an example. 1, okay? So she says, okay, my counter example, counter, C-O-U-N-T-E-R, can't spell, counter example, Haley says, okay, what if n is 1? And if I take 1 and I square it, is that greater than 1? No, because it's 1 is greater than 1, and 1 is not greater than 1. 1 is equal to 1. So there's a counter example. Okay. We also did this morning, we did another counter example where, like, let's say n is 0.5, right? If I take 0.5 and square it, what is 0.5 squared? Or what's half to 0.25? Is 0.25 greater than 0.5? No, right? You only have to provide one counterexample, because if you provide one, then we're saying that that's no longer a true statement, okay? But I just gave you two just so that you can see that, okay? All right? So only one counterexample to prove it false, okay? All right, this next one you have to kind of think about a little bit, okay? This is the last one. If JK, I'll give you a second to write it down. If JK equals KL, then K is the midpoint of JL. What? If JK equals KL, then K is the midpoint of JL. Okay? All right. K is the midpoint of JL. So what they want to put in your mind is this happening, okay? If JK, that's this length here, is equal to KL, then K is the midpoint, right? Okay, that's the picture that they want to put in your mind, okay? Is there any way of me drawing that thing where JK and KL are exactly the same length, but K is not a midpoint?
Parallel lines on a, like, coordinate plane.
Okay, but if they're parallel lines though, like this is JK and this is KL, this has to be the same K though, right? Like they have to be touching each other.
Just make it like a smaller angle.
What?
A smaller angle.
Yeah, so Jalen said, okay, let's make it angle style. Ugh, that was a really bad line here. I'll try to make them the same length here. Okay, so here's J, and let's call this K, and let's call this L. And this is the same length as that one, right? JK is the same as KL. But is K a midpoint? No, because K is not a midpoint because it's not all one segment, right? So it's no longer in the middle. I mean, it kind of is in the middle of the angle, but we don't call him a midpoint if it's an angle, right? We only call it a midpoint if it's a segment. So this is what this is an example of a counterexample that is a drawing. Okay, that's an example of a drawing counterexample. This guy was an example of a number counterexample. Does that make sense? Count X. I don't know why I put count X. Counter X. Counterexample that's a drawing, a counterexample that's a number. Okay, any of those will work. Okay, happy with that?
Yep.
All right, homework assignment. Did I give that to you already? Yes, this guy right here. 14 through 44, evens, and 60 and 62. Most of the time it's just patterns. Okay, everybody say bye, Libby.
Bye,